All right, so welcome everybody. So I think we'll have some people streaming in over the next little while. I think two of our presenters are coming shortly. So my name is Nick, and welcome to the Hydrogen Showcase. The intent is to present you with really a view of what's going on in the hydrogen industry, both from a world perspective and especially Canada, especially what's the opportunity. So we have a great group of guests. So we'll start off with Maggie Hanna, who will give us a bit of a basic overview of hydrogen to get us all on the same level. And David Layzell will present his work on the transition accelerator of how we can actually more quickly grow an economy in Canada and what are some of those opportunities. And then we'll have a group of industry who will actually show us what they're up to on the ground. Oh, actually, here's Badr right now. I'll let him in. And we'll start off with Shannon Halliday from Htech. They have hydrogen fueling infrastructure in several cities in Canada, as well as in the US. We'll have Badr Abduljawad, who will talk about Hydra energy, and they're actually converting trucks right now to run on hydrogen and supplying them with hydrogen, as well as Matt Fairlie, who from Next Hydrogen over in Ontario. So they're actually supplying Canadian Tire with some hydrogen made off the Ontario grid, taking advantage of wind power over there. And we'll finish off with Kathleen O'Neill, who is building an innovative new technology that'll be a big game changer at New Wave Hydrogen. And after that, we'll have a little bit breakout room, and then we'll have a big group discussion at the end. And after each presentation, we'll have a short question period. And one thing we'll use is a tool called Slido. So if you look in the chat, I put a link. So when we come to the question periods, you can click on that link and you can actually put in your questions, and you can see everybody else's questions. And that way we'll take the questions that have the most interest from the group. And that's how we'll run the session today. All right, and if there's any issues or problems, we have the chat open, so anybody can put something in the chat. If Slido doesn't work for you, you can also put your questions on the chat. We'll make sure it gets into Slido. So without further ado, we'll start off with Maggie, and let me just get your slides ready shortly.
Greetings, everybody. Welcome. And my job here is to set the stage with some hydrogen basics to make sure that everybody is on the same page for the rock star presenters that are yet to come. So that's my job. So as soon as the slides come up, we'll get at it. All right.
There you go.
Excellent. Okay, so next slide, please. And so what is hydrogen anyway? You know, it is the first element on the periodic table, and it's the smallest one we have. On the left, you can see that hydrogen doesn't hang out as a single atom, but it hangs out as a molecule made of two atoms of hydrogen bonded together into H2. That hydrogen bond is critical because that is where the energy is stored. Next. There is a lot of hydrogen in the universe. Next there, Nick. About 73% of all of the atoms, about 73% of all the atoms in the universe are hydrogen, and it is the fuel of the universe. Next. However, there's very little hydrogen roaming around by itself on Earth. Most of what we have is tied up in the ocean water. So we have to actually use energy to make it. And hydrogen is therefore not an energy source, it's an energy carrier. Or it can be called a fuel as well. Next. So take some time to take a look at the hydrocarbon chemical structures. The first three molecules represent coal, oil, and natural gas. And you can see there's lots of carbon atoms in there. And when we burn these for energy, CO2 gets pooped off into the atmosphere. But where does the energy actually come from? Most of the energy is held in the hydrogen bonds, hydrogen to carbon bonds. And when we break those bonds by burning hydrocarbons, we release the energy for our use, right? So why hydrogen? Well, shown with a red arrow, there are no carbons at all in hydrogen. So when we break the hydrogen bond for energy, no CO2 results, and that only water, and that's why hydrogen. Next. So the world is moving away from burning hydrocarbons because of climate change and the resulting weather weirding. This pie chart shows us the effects of various greenhouse gases currently overheating our atmosphere. Look at the biggest blue pie slice on the right. The lion's share of atmospheric overheating comes from excess CO2 emissions from burning fossil fuels for energy, 62% on a worldwide basis, in fact. Only 20% of those emissions are actually emitted by oil companies, though, when they make the fuels for us. The other 80% comes out of our own tailpipes and our own chimneys. If we could use hydrogen for our energy needs, our only emission would be water. Next. So why does CO2 warm up the atmosphere anyway? Well, our planet has an ancient natural blanket of heat trapping gases in the atmosphere, which is dominantly CO2. And this natural blanket keeps the Earth about 30 degrees Celsius warmer than it would be otherwise. And that's a good thing, right? It's natural. And it works just like a blanket that traps your body heat on a cold night. So what the heck's the problem anyway? Next. Well, the problem is by digging up and burning coal and oil and natural gas, which release large quantities of CO2, we are wrapping an extra blanket of heat trapping gases around the planet. And just like you would if your grandma snuck into your room at night and put an extra down comforter over you, you'd wake up sweating too. Next. So we're trying to keep our planet under 2 degrees C of extra atmospheric heating, which doesn't sound like much because we think, it's just about air temperature outside. No big deal, right? But that's not the way it works. That's weather. That's not climate. Climate is measured as an average of the weather over 20 to 30 years, and it works more like a fever in your body. If your body ran an extra, like a 2 degrees chronic fever of say 39 Celsius, or for us older folks, 102 Fahrenheit, then you wouldn't be operating very well either. Next. So what can we use hydrogen for? There's a lot of things that electricity does really well, but things it just doesn't do very well, but hydrogen does. So the biggies are highlighted in yellow on the slide, and they include heavy long distance transport like freight trucks, buses, trains, and shipping, and eventually planes. Industrial heat like for steel and cement making. Seasonal large scale electrical power storage. Hydrogen is the only thing we've got. Space and water heating, and feedstock for fertilizer production and other chemistries. Next. The world is getting onto this now, and some countries are moving faster than others. Over 25 countries in the world have already published their hydrogen strategy. And in December, Canada released our federal hydrogen strategy, 141 pages, which was very well received, I might say. David Layzell, who you will hear from next, had a lot to do with that document. Next. So how do we make hydrogen? Like, there is a color taxonomy which speaks to the process for making it. And this chart shows you how many kilograms of CO2 is produced for every kilogram of hydrogen that is made. Now, I want you to notice a couple of things. There are ranges of carbon footprint for each of these types of hydrogen production, depending on the circumstances. So you can see that what really matters is not so much the color of the hydrogen, but it's the actual carbon footprint. Anything less than 5 kilograms of CO2 is considered to be low carbon hydrogen by the European Union. Still, I think it's useful to know what the colors mean. So let's get into that. Generally, the 3 lowest carbon footprint hydrogen processes are pink, which uses nuclear electricity for electrolysis, which splits water into hydrogen and oxygen, and also green, which uses renewable electricity from hydro, wind, solar, tidal, wave, geothermal, to do the same thing. And also blue, which uses natural gas and water to make hydrogen and CO2, on the condition that that CO2 is sequestered permanently in the ground. They are all considered low carbon hydrogen by the EU's definition. So that's the first 3. Now let's look at the middle 3, which also have the possibility to produce low carbon hydrogen by electrolysis. But They also can be higher carbon, as they have much more carbon footprint variability depending on the circumstances. So these are turquoise. This is where we heat up natural gas in a certain way and make hydrogen and or not known, but less. White is byproduct hydrogen from industrial processes like chloralkali plants, which make chlorine and sodium hydroxide. And yellow, which is about using grid electricity for electrolysis. But the grids can have highly variable footprints of carbon footprints, as you can see from the length of the yellow bar. The last two processes have the highest carbon footprints in their processes because they both use hydrocarbon feedstocks and they both poop the resulting CO2 off into the atmosphere. Gray uses methane and water, and brown uses coal. So today, about 95% of the world's hydrogen is produced by gray and brown processes today. About 3% is blue, about 2% is green. So we really have a lot, and I mean a lot, of room for improvement. Next. So turning to the Canadian domestic hydrogen market now, we estimate by 2050, Canada alone will need to produce about 7 times the amount of hydrogen that we do today. This means going from 8,000 tons of hydrogen a day to 58,000 tons a day. Now, that's a big domestic market. How the heck are we going to get that done? Well, here in Canada, we are absolutely blessed with resource endowments to make hydrogen. Green dots are for the hydro dam powered green hydrogen in Quebec, Manitoba, and to some extent BC. That is to say, using renewable hydroelectricity to split water into hydrogen and oxygen. The big blue dots on the map are represent blue hydrogen in Alberta, BC, and Saskatchewan. And this is where we have natural gas resources to actually make blue hydrogen. That is to say, heating up natural gas with a bit of nickel catalyst in there. And out comes pure CO2 emissions needed for sequestration back into the earth and hydrogen. The pink dots are for nuclear electricity used for electrolysis of water to make pink hydrogen. Nuclear is actually Ontario's big expertise, but also New Brunswick and Quebec as well. Next. So what's happening internationally? Well, this chart plots hydrogen production potential against domestic hydrogen consumption. Where the country wants to be is in the upper left quadrant. This is where their ability to produce hydrogen outstrips their domestic consumption, and thereby they've got extra to export. Countries on the bottom right consume more hydrogen than they can possibly make, so they are the importers. Now, we are starting to see an international movement of hydrogen along the green arrow from the countries with enough hydrogen to countries without. Note that Canada, highlighted in yellow here, is in the exporter category. We think we should be able to export at least as much as Canada's domestic hydrogen requirement. Next. So what do we have going on in Alberta so far? Well, this is the Shell Quest project, which sequesters 1 million tons, that's to say a megaton of CO2 every year in the earth, and has been doing that for the last 5 years. It's just north of Fort Saskatchewan in Alberta. Next. The Industrial Heartland. Next one, Nick. Well, the Industrial Heartland Working Group have set the stage to be Canada's first hydrogen hub northeast of Edmonton, and is working with the Transition Accelerator. And Dave Layzell will say more about that right after this presentation is done. Next. So the Htech project is, and that's out of the University of Calgary, the CESAR group, is building 2 big hydrogen fuel cell powered Class 8 freight trucks for test runs between Calgary and Edmonton starting this fall. Now, I want you to notice the range of companies in this collaboration. Like, collaboration is the only way we're going to get this hydrogen economy thing done because of the chicken and egg nature of supply and demand when it comes to hydrogen. Hydra is another one of our corporate gems involved in hydrogen trucking, as you will be hearing from the President Badr today. So that's pretty lucky. Next. Alberta also has the Alberta Carbon Trunk Line, pictured here in orange, and it's the longest CO2 pipeline in the world. They actually pay $20 a ton for CO2 and then inject it into the Clive pool near Red Deer to produce another 1 billion barrels of oil that would not otherwise be recoverable, and sequestering some of the CO2 in that process. Next. ATCO is working on blending hydrogen into natural gas pipelines in the city of Fort Saskatchewan.
Maggie, your audio just went out.
My audio just went out. Why? Can you hear me? Am I back? Oh, I just got your internet connection is unstable sign. Can you hear me now?
Yeah, loud and clear now.
Okay. Yeah, loud and clear now. Okay. So, so let's just go back to, let's just do this. So if you didn't hear me, I just wanted to say that ATCO is mixing 5% hydrogen into their natural gas lines. And they hope to ramp that up to about 20%. So now we'll go next. Oh, and so bottom line is, we in Alberta, we have a good start, but we have a lot of work to do collectively. Some jobs to generate and some carbon to mitigate. But if we get this post-carbon energy transition stuff right, the future generations will look back at us and laugh, saying, I can't believe our ancestors actually burned this valuable stuff. It's good for so many other things. You're really in for a treat today, hearing from some of the movers and shakers here in Canada. And that is, they're the people that are actually making this happen. So finally, thank you for your kind attention. Here are my coordinates. I was going to say feel free to take a screen capture, but it's too late now. And reach out if you have any further questions and queries down the line. I will actually put my coordinates in the chat box, so you can grab them there. Thank you, everybody. Hope that set the stage for you.
Perfect. Thank you, Maggie. So now we'll have a short question period. And I see one of the top questions right now is, can you read the question, Maggie? I'm surprised green. Yeah, I'm surprised green renewable.
I'm surprised green renewable electrolysis has some carbon emission from production. What is the source of the CO2 by producing green hydrogen? So the carbon footprint of a thing is best looked at on a life cycle basis. So on a life cycle basis, and that's what that chart I showed you was, a life cycle basis. So it includes building the equipment. It includes moving the equipment on the site. It also includes for things like if you're using hydro for your power to make that green hydrogen. Hydro dams have a dirty little secret. They emit methane and CO2. Northern climates, they emit more CO2 than methane, and southern ones, closer to the equator, more methane than CO2, but still, that's included in the carbon footprint. So I hope that answers your question. Next question, does the amount of carbon in coal, oil, and gas correspond to the amount of carbon dioxide created when those fuels are burned? So yeah, absolutely. The more carbon is in coal. Coal is higher carbon, higher proportion of carbon with respect to the hydrogen in it. Oil is next and natural gas is next. So that's absolutely correct. What does the color refer to? Just the name for a type of fuel? Not exactly. The color is more about how each of those how hydrogen is produced by those different methods, right? So if you're using natural gas and water together and heating it up in a steam methane reformer, that's called blue. When you sequester the CO2 in the ground, that's called blue hydrogen, right? So the different hydrogens have different names depending on how that hydrogen is made. Next. Do green and blue hydrogen have any waste products created during the process of using the fuel, like nuclear waste created from nuclear energy? So green hydrogen, not so much. Blue hydrogen, yeah, there is a waste, but we sequester 90% of that in the ground. It's the CO2 that goes into carbon into at least 2 kilometers deep in the ground and in the earth. And so that's a waste product, but we know how to deal with it. And that actually makes blue hydrogen a very low carbon footprint type of hydrogen. Nuclear waste, absolutely, is a waste from making the power for paint. And at the same time, nuclear waste isn't as big a deal as a lot of other kinds of waste. It's very compact, it's very small, we know how to deal with it. And we have different kinds of nuclear reactors coming online now that actually can burn that nuclear waste and take more energy out of it. So I'm actually a fan of nuclear. Let's see, what else we got here? Does the CO2 pipeline work by pushing the oil through faster than it would come out by itself, or in place of using another type of fuel to push out the oil? Okay, so we're talking, I'm guessing here, but I think we're talking about the Clive pool. And basically, when you put CO2 into the reservoir with the oil, the CO2 dissolves into the oil, reduces the viscosity so that the more oil can be pumped out. Like it takes it from being quite thick to a lot thinner, and then we can produce it a lot easier. So I hope that answers your question.
Thank you, Maggie. Now we'll hear from David Layzell. So David, if you want to share your screen and put your slides up.
Thanks, yep. Maggie. That's great. Thanks, Nick. I will share my screen here. What I'd like to do is follow on from some of the discussion that Maggie, an introduction that Maggie provided, and talk a bit about how to build a fuel hydrogen economy and the importance then that we see of hydrogen hubs. So to put this in perspective, let's, as Maggie mentioned before, we already have a pretty significant hydrogen production in Canada today. It works out to about 8,200 tons of hydrogen every day. The hydrogen, virtually all of it, is made from fossil fuels, mostly methane, natural gas. And in making that hydrogen, carbon dioxide is released to the atmosphere. This is called gray hydrogen. That hydrogen is used to make industrial feedstocks, fertilizers for agriculture, especially ammonia, and as well as fuels for transportation and other chemicals and materials. And if fuels for transportation, hydrogen is used to crack bitumen into synthetic crude oil, but also convert all kinds of crude oil into gasoline and diesel fuel. In a new net zero energy system, we are looking at fossil fuels and biomass. Kathleen, you got your sound on. The CO2 would be, of course, produced, but we need to capture that CO2 and sequester it. And that's called blue hydrogen. So essentially it's similar to this process, but we're not releasing the CO2 to the atmosphere. And if you use it from a biomass source, you can actually get negative carbon emissions from that process. As Maggie said, you can also make green hydrogen from renewables or nuclear, and that's sometimes called pink and other colors, but we're called electrolysis based. And you can also get hydrogen. We're going to hear from Badr from chlor-alkali plants where hydrogen's a byproduct. In all ways, these have much lower or no carbon emissions than the gray hydrogen, and it can be used not only as an industrial feedstock, but the goal is to provide this hydrogen for export to other jurisdictions, overseas as well as the United States, or to provide it as a fuel for supporting transportation, building, heating, industry, and even power generation within Canada. And it was power generation, so you could actually hydrogen become a form of long-term energy storage, electricity storage, because you can use electricity to make hydrogen and then use hydrogen to make electricity again. Now, the good news is that Canada has a real competitive advantage in this space. Canada's this is a Japanese study from about 2.5 years ago, where they've looked at all the countries on the Pacific Rim countries and identified Canada, the ones in yellow on here, as one of the lowest places in the world to make blue hydrogen that's made from natural gas. And certainly of all of the countries they looked at, the lowest cost in the world for making green hydrogen. But what you'll notice here is that blue hydrogen today tends to be less expensive to make than green hydrogen. And indeed in Alberta and in Western Canada, blue hydrogen is about half the wholesale cost of diesel and about 1/3 the retail cost. So that opens up a really interesting opportunity for trying to grow a hydrogen economy with those kinds of feedstocks. But the challenge with hydrogen is that it's a gas. It's really, we could make it quite inexpensive, lower than the cost of diesel, but it's more expensive to move and store around than liquids. And the other thing is the economic improves though with scale. So as you start moving more hydrogen around and having greater use of hydrogen, the actual cost comes down quite dramatically. So our analysis here is we really have to go big or go home. We have to get to the scale quickly. So what we are arguing is we need to focus on hydrogen hubs, places where we have low cost hydrogen production, substantial nearby market demand, and a cost-effective connection between the supply and the demand. The one that's most obvious is pipelines, especially if we can get to scale where pipelines make sense. And we need engaged industry, governments, and academics working together to put this new value chain in place. We've been looking at where to do this across Canada. One of the areas we see as a significant opportunity is in Alberta, around areas where we already have large-scale industrial blue hydrogen production. And this is where includes with the cost of CO2 capture, is that we can make hydrogen at about $1.50 a kilogram. And we can then piggyback on that kind of industrial infrastructure, pull a pipeline off and provide the hydrogen to buses and trucks, to trains, for transportation, space heating for homes or commercial buildings, and even possibly for power generation. And this pipeline, the same infrastructure, could be used to bring green hydrogen to market as well, if the pipeline goes through a region where we have good green hydrogen production. The idea is to have pipelines connect to new markets, rapidly grow these demands for this hydrogen, and also attract an opportunity to attract internationally hydrogen using industries and original equipment manufacturers that are interested in benefiting and growing their business through hydrogen supply and demand for that hydrogen. Within Alberta, one of the most promising areas is right near Edmonton, and we call it the Greater Edmonton Hydrogen Hub. And it already has a hydrogen pipeline that's shown here. Maggie talked a bit. It has the Quest CO2 line is up here, and it has a Alberta Carbon trunk line for enhanced oil recovery here. So 2 pipelines that carry away the byproduct, the CO2 that is you create when you make blue hydrogen, and a number of companies that would be using that hydrogen. And in fact, 3 of the companies already now are producing a blue hydrogen and putting the CO2 in the pipeline. So what we see here is the opportunity to find markets, potential market sizes. And I'll give you an example here. This is the end of the hydrogen pipeline. This is the city of Edmonton and its ring road. What we have is the red dots are the major private trucking fleets. These are the big commercial trucking fleets. And the little gas pumps there are existing diesel fuel stations for fueling those large trucking fleets. We also have here municipal fueling for buses, the fueling stations for municipal buses, for garbage trucks in this area. These are, snow plows and gravel trucks, etc., that the city owns, and the city of Edmonton is quite interested in converting a significant proportion of their fleet to hydrogen over the next few years. And then we also have here injection ports where high pressure natural gas pipelines are dropped to lower pressure for distribution for residential and commercial heating throughout the city. And so these are the points where we could inject hydrogen in and mix hydrogen in, as is already being done in Fort Saskatchewan, the possibilities to do it in Edmonton as well. So we've estimated in the work we've been doing is that there's a potential in the whole area for transportation demand of about 670 tons of hydrogen a day. This is just in the Edmonton region. There's potential for space heat in the 1,500 tons a day, and that would be, of course, higher in the winter than in the summer, and potential for export in many thousands of tons per day. And the important thing to note is that virtually all of the demand for these occurs on two main corridors, both anchored in where we can produce low-cost blue hydrogen. One is a corridor that comes diagonally through Edmonton and heads down towards the airport, another one across the top of the city. So the conclusion here is that hydrogen hubs are needed in order to get to scale and to build a resilient new hydrogen energy system, an energy system where the production of we can get to the sufficient scale of production to keep the price low, and we can get to a significant scale of demand in order to be able to have a cost-effective linkage of pipelines typically, but not absolutely necessarily, that would link the supply to demand. And these should be deployed at strategic locations across Canada. Edmonton is one location where we see opportunities, certainly Prince George, we're going to hear about some exciting opportunities there. Sarnia, Ontario, there's places in Quebec, there's places in Eastern Canada, a number of other places, I would say in British Columbia and in Alberta, that we could actually build significant demand centers around. And then we need to grow these demand centers and interconnect them to serve other communities. And we see this as a key part of the strategy, the pathway to a net zero future. Thank you.
All right, David, we'll start off with some questions. I think the first question is about hydrogen embrittlement and a problem for pipelines. Can you speak to that?
Sure. The hydrogen embrittlement is a problem for pipelines, especially if it's a carbon steel, high carbon steel, because the hydrogen gets into the steel and starts pulling the carbon molecules out and causes embrittlement. There's a 50 kilometer long pipeline in Edmonton now. It was the red line on my charts. That is a steel pipeline. And it's basically 98%, 99% hydrogen. So steel works fine for hydrogen as long as you got the right kind of steel. Where there is a lot of interest now in taking existing natural gas pipeline infrastructure and repurposing it, especially if it's abandoned infrastructure, repurposing it for hydrogen. There are some companies that are looking putting plastic liners down the pipeline that would use the pipeline corridor and basically get a second life out of that of other infrastructure. And there's even a possibility of putting sort of a pig down the line and spraying on a chemical or basically a sealant that would keep the hydrogen away from the steel. There's a lot of work being done on the whole issue of how do you take some existing infrastructure we have today and over the next 30 years move it to infrastructure that would support a hydrogen economy. Second question, what's holding this up? The biggest thing is that we are really trying here to create a new energy system. And I think the problem in hydrogen in the past has been we've had a vicious cycle. We don't have any hydrogen infrastructure because we don't have any vehicles, and we don't have any vehicles because we don't have the infrastructure. And so the idea that we've been working on is where are the opportunities in Canada where we can break that vicious cycle and create a virtuous cycle where, and we would argue it's around places that already have significant hydrogen production where we already have either blue hydrogen production or hydrogen production, the gray that could be made blue and sequestered, or really extra electricity that could be used to make a green hydrogen. Or another exciting opportunity is places where we actually are already producing significant amount of byproduct hydrogen, and it could be tapped off and used to support hydrogen economy. So, and then we can then break that and then build demand around those locations to try to build out around nodes or hubs across Canada, really significant hydrogen demand.
Thank you, David. All right, up next will be Shannon Halliday with Htech. If you can share your slides.
Here. Thank you very much, Nick, for inviting me, and thanks, David and Maggie, for your presentations. They're super informative as usual, and I've got a number of notes written down where I want to perhaps borrow some of your slides, if that's okay. Shannon Halliday, I'm the VP of Sales and Marketing with Htech. And I've been in the industry, I started in the industry ages ago and then recently came back and joined Htech in September of last year. And a brief introduction to Htech: we design, build, and operate hydrogen production facilities, distribution systems, and fueling stations. And we've been in the industry since 2005. And it was, in fact, in the spring of 2005 when the Ford Focus fuel cell vehicles were first delivered to Vancouver. And I was working for Natural Resources Canada at the time, and we had funded part of this station. And my office was based at the National Research Council building. And if you walked out the front, if you were lucky, you could walk towards the compound and it wouldn't be locked. Or you had to walk down the freakishly long hallways of the National Research Council, past the hydrogen safe labs, into the back towards the forest, and tucked in was this fueling station. And there'd usually be quite a lot of researchers in their lab coats milling about. And although there was really excellent learnings that were happening as part of this station, it is not something that would inspire a quick commercial uptake. Fast forward to the present, this is one of our stations that we opened last year, and our hydrogen delivery truck is delivering, this was just a few weeks ago, is delivering hydrogen and power cubes to the station. And if you look here at the manhole on just beside the truck, and then in the next picture at the manhole, what do you see in the background? You see a McDonald's, and nothing says that you have achieved a certain level of public confidence like being in spitting distance from a McDonald's. There's no lock compounds, there's no lab coats. We've come a long way in the last 15 years. And so another way of looking at Htech in the value chain is looking at it as the glue. And as Maggie mentioned, you can produce hydrogen in a variety of ways. And that would be the clean energy supply at the beginning. And Htech is, we currently have green hydrogen production. We are investigating blue hydrogen projects as well as more electrolysis projects. And at Htech, we have two business platforms. One is the infrastructure platform where we produce, distribute, and dispense. And the other is our technology solutions platform where we help others with their hydrogen needs. And that can be from project development, design, engineering, specialty and packaged products, operations and logistics support. And in the last box here, we work in partnership with hydrogen consumers. And as Maggie mentioned, all of this is about collaboration. And so here are some of our partners listed on the bottom. And at the top are some of the end user markets, and we work with all of them. We have a station in Quebec with Arnoa right now. We have 2 more under construction in Quebec, and we have 4 stations in operation in BC, 2 with Shell and 2 with 7-Eleven. 5 more are in construction or under development. The next one to open will be a 7-Eleven station in Kelowna. And these stations that we have in operation right now are light duty stations, but the ones we're opening will be a combination of light duty and medium duty and heavy duty. We also have a station in California with electrolysis on site that is opening up in this summer. And I just wanted to highlight why light duty is important. Is it allows options. So options for the public. It also increases public awareness, it advances codes and standards, and all of the cost benefits realized in light duty applications are then applied into these larger applications like buses, trucks, and trains. And as David mentioned, scaling up is really important. And that's one of the things that light duty allows us to do. And so I just wanted to share a few pictures of these hydrogen stations that we operate. So this is the picture of a Shell station in Vancouver. It was Canada's first retail hydrogen station. It was designed, built, owned, and operated by Htech. This was opened in June 2018. This is a 7-Eleven station selling Esso branded gasoline and now Htech hydrogen. And this is a picture of our CEO, Colin Armstrong. And in closing, I wanted to share a few words of wisdom from Brene Brown. I want to be in the arena. I want to be brave with my life. And when we make the choice to dare greatly, we sign up to get our butts kicked. We can choose courage or we can choose comfort, but we can't have both, not at the same time. And courage is something I've seen in ample supply in this industry, and I'm really proud to be a part of it. And for anyone who is presently comfortable, would you take the chance to choose courage and join us in this incredible energy transition? And so here are my details right now if you want to take a quick screenshot, and I'll stop sharing my slides. Thank you.
Thank you, Shannon. So I'll just put on our Slido and we'll see if there's any questions relating to your segment. So if anybody can't use Slido, please put your questions in the chat and we'll transfer them over.
So I just have a quick question because I tried to put in Slido anyway. So and Shannon, I'm wondering what does it cost to put a hydrogen station in, and what are you selling the hydrogen for these days?
Well, at the pumps right now in BC, we're selling the hydrogen for $12.75. So it works out a little bit cheaper to fuel up your hydrogen car than your gasoline car for the same mileage. In Quebec, we're selling the hydrogen. It's Arnois that sets the price for the hydrogen in Quebec, and presently they're selling for, I think it's $18.75 a kilogram.
Wow.
And then the cost of the stations really depends from a mobile fueling station to to a full-blown station. So you could be the cost can really vary depending on what it is that you want to install. You've muted again, Maggie, just in case you wanted to add anything there.
Just telling my son to be quiet.
I just told my son, no playing with knives while I'm on this phone call.
So also I'm wondering about Htech in terms of, are you planning to go to other cities soon? Are you going to build out in just Vancouver for a while? Or
oh yeah, absolutely. We've got our project in Alberta, and I forgot to mention it. I had it in my notes and I forgot that we're part of the Htech project, which is really exciting. We're exploring more projects in Vancouver. We get asked, pretty regularly, can I drive my hydrogen car to Alberta? And right now we have to say no, but we hope in the future that will be a possibility. We are working on a ports project in Los Angeles. We're working on a ports project here we're working on developing a couple ports projects in Canada. Like I said, we've got the 2 more stations that we're opening in Quebec, but we have another 4 on top of that are planned. And so it's really around this hub concept that David mentioned, that where this hub of activities are happening. And for example, with one of the projects that we're working at with the port, so that will be a light duty and medium duty, but then that facilitates hydrogen into the onshore operations with the port. And then, it's not a big step to then look at offshore operations as well. And so all of this starts scaling up and creating that market for the hydrogen. So we're exploring projects all over the country, and we're open to working with anybody who wants some hydrogen infrastructure or help developing their own.
Perfect. Thank you, Shannon. And now we'll move over to Badr. If you can share your screens, and if you have any issues, I can put your slides up as well.
Hi, everyone. My name is Badr. It's nice talking about Hydra today. Thank you, Maggie, and everyone for talking a little bit about it. I'll start off by, I guess, Hydra was founded in 2012, and it was founded on the idea of actually being a pioneer in solving this chicken and egg problem that everyone talks about in hydrogen. And we do so by bringing basically the supply of hydrogen and the demand of hydrogen together. And we do so by using it for commercial fleets. And what is the offer that Hydra brings to the table to these fleets? Well, we bring them hydrogen as a service, and we do that by being able to help them, these fleet operators reduce fuel costs, emissions at no upfront cost. So Hydra retrofits these existing trucks at no upfront cost without sacrificing any performance in terms of power, range, or payload. And in exchange, Hydra gets an exclusive agreement to supply hydrogen fuel at a cost that is lower than diesel, providing the fuel savings and emission reductions. So there's no loss in power or torque, no loss in payload, as I've already mentioned, and you guys can see that from our testing results. This retrofit is basically just adding a hydrogen computer that talks to the diesel computer with some hydrogen tanks and hydrogen injectors. And this basically co-combusts with the diesel, so it is a gaseous fuel. And then Hydra's business model is to go with and capture some hydrogen, waste hydrogen. And as Maggie touched on this a bit earlier, in BC, this is considered green hydrogen. And it's also, I guess, considered white hydrogen because it is a byproduct. So we will expand this business model at a more cost-effective manner. We include hydrogen for electrolysis. It meets our renewable gas content by reducing carbon tax as well. Our first project is 65 dual fuel hydrogen semi-trucks. Our first station, the first hydrogen station, is actually would be the largest in the world. And now it's about six times larger than the fueling station currently in Shanghai. And yeah, I'm open to questions.
I think we still have some questions regarding the previous slides. So does anybody have questions for Badr around hydrogen as a service? And any questions from our panel, Maggie or David?
Well, yeah, I got a question, Badr. I'm wondering, are you guys open to expanding your business model to actually sell the kits so that this could go a little farther, a little faster? I just wonder.
No, currently we're just exploring the business model around basically where we have hydrogen supply, and we're not expanding the business model at the moment to just sell the kits on their own. It kind of comes as a package.
There's a quick question of. There's a quick question about, will you be expanding to the U.S. or just keeping to the Canadian market for now?
Yes, no, we are exploring. Yes, we will be expanding to. Yes, we're exploring those similar kind of waste hydrogen potentials with chemical manufacturers all over.
Maggie, your next question.
So what I was thinking is that it, you know, and I know you said no, but what I'm thinking is if you actually sold your kits, that would enable the chicken and an egg problem to be solved in a lot more places. You know, because what I love about your tech is that if there's no hydrogen around, the trucks just swap over to diesel all by themselves. It's like a Prius, you know, like a Prius does. Like you don't even have to press a button. And if we had that in places where we're trying to put in fueling stations, in the stage between where we have just a few fueling stations and a whole bunch, that would be such an awesome advantage for actually kicking off the hydrogen chicken and egg problem.
Correct. So I guess our biggest concern a lot of times is if the kits isn't sold in an area where there is hydrogen on both ends, then the idea behind saving fuel costs won't work the same way. So it would be on a I guess a different basis for that reason. So this is why at the moment we're just keeping it towards hydrogen as a service to be able to ensure that they can get the reduced fuel costs.
Mm-hmm. No, I understand that. It's just that, like here in Alberta, for example, we got to put hydrogen stations in, right? And if we had access to your tech, then we could have retrofit the old fleets with hydrogen diesel biofuel, and it would eliminate the hydrogen anxiety because we haven't got enough fuel stations yet. And then if we had your kits as well, it actually makes the existing fleet useful in terms of being able to use hydrogen. And then those people are really get used to it. And then the next truck they buy could be a full hydrogen fuel cell truck. So that's my rationale.
No, that's true. I've actually we've worked we've been in touch with David actually Layzell here to do a pilot project on that in Alberta. We just it's just he asked me the question is, are we selling our sex immediately our kits today? And it's just not as it stands today, but we are working on a pilot with David to address that issue. So it is a good point.
Oh, that's so good to hear. Good to hear, Badr. Thanks.
All right, thank you, Badr. And now we'll have Matt Fairlie up with the next presentation. So
okay, well, again, thanks, Nick, for inviting us to join this showcase and the opportunity to introduce Next Hydrogen to your audience. Next Hydrogen is a Canadian company. It's based in Ontario, founded in about 12 years ago. The founders, it was actually a marriage of wind farm developers and some technology guys from the electrolysis industry. And the wind guys sort of set out the challenge. They wanted really a purpose-built, purpose-designed electrolyzer for integration into renewable energy. And I think everyone on the call is probably acquainted with what that requires. It means large scale. It means flexibility. It means operating intermittently. And the team took on this challenge, and 12 years later, we're here today with units in the field and a rather interesting patented technology that I'll talk about a little bit later. Where am I today? I'm actually at a Canadian Tire site in Bolton, Ontario, where we're commissioning a 300 normal cubic meter an hour plant. That's a plant that produces about 650 kilograms a day if it's operating continuously. The plant, of course, operates around electricity market opportunities, so it's not operating continuously. Canadian Tire's purchased 3 of our units. The hydrogen is used to provide fuel for a fleet of forklifts. These are fuel cell powered forklifts. And the interesting thing about this project and what we're doing with Canadian Tire, the project started about 5 years ago. There's no government funding. This is all run off CBA, which Canadian Tire has. Though Canadian Tire is a little bit different in that they were really curious about hydrogen and how it could be scaled up as an infrastructure using electrolysis, producing green hydrogen. They also have a significant presence in retail transportation fuels. So that's where we're at. We're operating systems here at Canadian Tire. We're scaling up the company. Of course, this is a great time to, one can say this is one of the, in the cycle, this is a good time to be in the hydrogen business. So we're pushing forward with building our company and expanding it. But I'll just talk a little bit about our electrolysis technology, and that's really our raison d'etre. This is what we bring to the market, and we think that it's a class winner here. So, as I said, the challenge given to the team was to develop a more flexible, more easily integrated electrolyzer, and that involves building at scale. Something that so multi-megawatts per unit, advanced enhanced dynamic response, and other things that one would expect in terms of what the market requires today. Now, the approach that our team did was actually a pretty dramatic departure from conventional electrolyzer architecture. So this is a picture of some of the internal components in the system. And the thing that I want to draw you to is those lung-shaped things above the circular thing. The circular thing is the cells that you normally see in an electrolyzer that produce the gas. It's a bipolar stack, so it's a stack of these things producing gas. But above it, we have built the gas cooling and gas liquid separation. So all of this is done on a cell-by-cell basis. And what that buys you is when you can, when you look at our system versus a conventional electrolyzer, and this is, I'm showing a conventional alkaline electrolyzer, we are also an alkaline electrolyzer, but our architecture can work in both alkaline and PEM. And the thing I want to draw your attention to is that the circulation of gas liquid system is actually circumferential and up through the cell, and whereas when you're looking at conventional systems, it's this very long path that goes along the axis of the electrolyzer, and of course one would expect that the process dynamics for the electrolyzer on the left hand side are going to be less favorable than the one on the right hand side, and that's really the architecture that we have developed. It's patented, it's unique. But you can see that it quickly to changes in power input. Yeah, we sell product currently in the 100 and 300 normal cubic meter hour sizes, and we are going to be in a position to release the NH500, I think, in 2022. So that gives you a quick outline, quick introduction to our company. And what we're doing. As I said, we're a manufacturer of electrolyzers, large scale, and likely in looking at where our roadmap leads to next, even larger units. So something we call the green, which is something that could be built into these dedicated renewable hydrogen projects. And again, we have the flexibility because of our architecture and our ability to operate at very high specific production rates, or what we call current density, allows us to produce a very capital efficient large scale plant. And with that, I'll take questions.
All right, so there's a couple quick questions about what's the retail cost of hydrogen, and there's a lot around the fact it's intermittent. So can you maybe answer how best to answer that question?
Okay, so there's a lot going on with hydrogen and electricity these days. If you look at these large dedicated projects, where, you know, in Australia or in Middle East, you're looking at renewable power prices less than 3 cents a kilowatt hour. You're getting in the $2 to $3 a kilogram production cost, based on a life cycle, you know, on a cost of hydrogen basis. If we're looking at something like Canadian Tire, what we're targeting is less than $10 a kilogram in the vehicle. So this is a purpose-built infrastructure. That means very good capital utilization. It means electricity rates according to ICI, that's without the global adjustment in Ontario, which would put it around 8 cents a kilowatt hour. So we're coming in less than, you know, less than $10 per kilogram in the forklift. So that includes the infrastructure, the compressors, the dispensers, etc.
Yeah, and last question, can you just give us an idea of what the utilization rate you're seeing at your plant at Canadian Tire? And I guess does it shift over the year, or what's that looking like? What's the percentage that you're...
Well, it's still early days here, so our utilization rate is very low, because they have been testing different fuel cell systems, and now we're transferring over to this larger system. So we're in a startup, but it's when this system is up later this year, there'll be a fleet of 150 forklifts. So utilization at 150, and we're expecting between 1 and 2 kilograms per. The utilization is going to be less than 50% on the rated size of the system. They do, however, have an outdoor fueling station, so we are looking at trucks to complement the forklifts inside, the material handling equipment inside. So there'll be some shuttle trucks, and then eventually there's as many has talked about in this session, you know, looking at the Ontario market, looking at the electricity market, and the market here, we believe that trucks are going to be a huge player in bringing hydrogen to Ontario, and also a huge player in decarbonization of transportation in Ontario. So hydrogen fuel cell trucks. So we'll be hopefully testing some of those in the next 12 months or so.
Perfect. Thank you, Matt. And if you can stop your screen sharing.
So hello, thank you. It's really a pleasure to be here today. I'm just really impressed with the panel and everyone. You have a really deep set of knowledge accumulated on this call today. So it's great to hear and learn from. I'm here to discuss a fundamentally new approach to clean hydrogen production. We call it a new wave in hydrogen production because we use shock waves to heat natural gas, and it's essentially a new energy paradigm in methane pyrolysis. See if I can get it to move. And it doesn't want to advance. Hold on. Why won't it work? Okay, now it's going. All right. So as you all know, the overarching goal is decarbonization, or the reduction of greenhouse gas emissions. And we need to do this quickly. I think everybody recognizes that It needs to be implemented on, are you hearing a feedback?
No, we're hearing just fine.
All right, thank you. Needs to be implemented on a very large scale in order to really forestall the cascading effects of climate change. So as showcased here today, one solution is transition to a hydrogen-fueled economy. But there are significant barriers in that transition that need to be overcome. And these are a few of the barriers. Our technology addresses these barriers. I'm hearing a major echo, which is...
Yeah, it's not carrying over with us, so you'll just have to, I guess, bear with it. It might be your headset.
All righty, no problem. So as you know, the current state of the art is steam methane reforming, or SMR, and over 90% of the world's hydrogen is produced via this method. But what isn't often known is that it also produces a good degree of CO2, and it has a high water demand. To rectify this, sometimes SMR is linked with carbon capture and storage, CCS, which is a good solution, but it adds other limitations. For Alberta, as example, you're lucky to have the Alberta carbon trunk line, you have CO2 pipelines in place, and you have a CCS storage area, but many areas in the world, or even in Canada, don't have that infrastructure in place. So for SMR to become a low impact technology, or greener or blue hydrogen production, it would require a parallel build out of CO2 pipelines and many different new storage infrastructure programs. And this is a really high cost, it's high risk, and it's going to take at least 10 to 20 years or more to have a significant impact. Due to the timelines and build out. So what we suggest is a fundamentally new approach to methane pyrolysis. I call our process a new energy paradigm because we don't need electricity to drive the reaction. We use the pressure inherent in a pressurized natural gas pipeline to drive the shock wave. So it's an efficient use of energy, and it can heat the natural gas to temperatures high enough to directly crack the methane molecule into hydrogen and solid carbon. And these are both valuable products. But as you can see, there's no water and no CO2 in the equation. This is a new application of wave rotors. Wave rotors have been around for about 50 years. So it's very low risk in terms of development. We're using a core component that's been known for 50 years. And in fact, all of the components in our process are standard and commercial. Patented innovation is the novel application. So we use wave rotors to achieve gas temperatures sufficient to directly crack methane into hydrogen. So it's a new use of this technology. Wave rotors envisioned as a rotating barrel of shock tubes with end plates that have ports in them. And when a closed port aligns with one of the shock tubes and we introduce a pressurized gas, the gas reflects off that closed port in a enclosed space and creates a shock wave. So it's kind of a supersonic speed compresses the gases and transfers heat. So we amplify the temperature of the natural gas. We have tremendous global partners, and which we've launched from Canada, starting a 2-year program, and hope to achieve a field pilot by the end of 2023. This 2-year program is funded both by industry and agencies in Canada as well as in Europe. Some of the partners on the call today and some of the agencies mentioned are actually on our partners on our team. AMTA and the Htech program are doing the hydrogen fuel truck trials, along with the transition accelerator and CESAR. They've been tremendous partners, and we're really excited to be working with them as well as everyone else. The NGIF is a natural gas innovation fund, the combination, a consortium of the natural gas producers and distributors in Canada. They're a co-founder of ours. Total in Europe is also a co-founder of ours, as well as GRT Gas, the major natural gas producers in Europe. We've been co-funded by ERA, the Emission Reduction Alberta, and we have so if you look at Canadian, European, and US hydrogen roadmaps, they emphasize 2 major production methods: SMR with CCS in this line, and electrolysis. Those are the 2 that are focused on in the hydrogen roadmaps the most. But as I said, there's barriers inherent in each of these technologies that actually slow the transition. And what we think we've done is create a technology that addresses these barriers. So we're accelerating the hydrogen transition. For SMR, as we discussed earlier, it produces CO2, or it has a high CCS risk. It's a very mature technology that has a low cost, but mostly at large scale. When you look at small scale distributed systems, such as those that will be needed for hydrogen fueling stations, for example, SMR gets fairly expensive. For electrolysis, it doesn't produce any CO2, and neither do we, but it has a really high, typically, electricity demand. So that electricity, yes?
If you want to maybe move to your last slide, and we'll quickly go to a quick question period.
Thank you. Okay. So in essence, really the key to our differentiation is that we can use the existing infrastructure, the natural gas distribution infrastructure. We don't need any new CO2 pipelines. We don't need any new hydrogen pipelines. We don't need carbon capture and sequestration. We use what's already existing to move the transition forward in a very quick manner. And it's the same with export. We don't need new types of ships or types of transition, chemical transitions to the hydrogen, because you can export the natural gas the same way we do right now and export the technology to produce hydrogen on demand wherever you have a pressurized pipeline. Okay, these are some of our end markets.
Okay. Thank you. And then we'll just, I'll just put Slido on, and then we've got a couple questions. So let me just bring them down to where you're at. So part of it is, what's the percentage, just an idea of the amount of energy used, and I guess what's the, how does this kind of hydrogen production compare to some of the other methods in the amount of CO2 and energy?
Okay, so the purity, the purity can be as high as 3 nines, 99.999, or 4 nines. In certain designs, we have different designs for different applications. So if we are admixing into a pipeline, like ATCO project was referred to earlier. We only need 20% of the hydro conversion to go to the pipeline. We can have a high purity 20%, or if we're going into a fuel station, we'd have very high purity, and we polish it using a pressure swing absorber, a PSA system. The energy required is very low, again, because we don't use electricity to drive the reaction. It's a shock wave driven reaction based on the pressure drop. We can install in any pressurized pipeline and use that letdown or that drop in pressure to drive the process.
Okay. I think your headphones cutting out a little bit, so that'll be it for questions. So we'll see if there's any last questions. I know there's any last questions before we complete. Please put it in the chat. And I think let's see what I think there's a last question or two here. I guess one question. Oh, sorry, who was that?
I was gonna say Hassan mentioned that he had some questions, but didn't get answers from everyone yet. Hassan, do you want to take the floor? We were in the room together.
Go for it.
Oh, okay. Yeah. Thanks, Badr. Yeah, I had a question for David Layzell, and then I had a question for Htech as well. David Layzell's question was around the capacity for CCS in Alberta, because there is Calgary, for example, in southern Alberta has some of the highest potential for solar globally. So at what point will we fill up all our reservoirs and we'll have to focus on electrolysis?
Well, I think there's a role for both of them, certainly in terms of filling up the reservoirs. We're running a study now where we're looking at all of the data, the geological data, to identify what's the size of the CCS potential within Alberta. It is very large. We have a lowest estimate. We're saying, look, do we have enough to cover us the next 10 to 15 years for setting up infrastructure that we know will provide 30 years worth of storage. And certainly we're talking many tens of millions of tons of CO2 per year could be cost effectively stored for 30 years or more. And so that's kind of what we're talking about deploying in the next 10 years or so. The actual numbers that we have so far point to potential for much larger storage than that. We live on very holy rocks in the Western Canadian Sedimentary Basin. There's lots of holes in these rocks, and so there's lots of storage space. In terms of, my sense is the economics of it, that green hydrogen is going to catch up with blue hydrogen relatively soon, especially in places like southern Alberta, southern Saskatchewan, with the combination of solar and wind, and especially if we can get electrolysis. And I'm very excited to learn a bit more about a next hydrogen project where their type of electrolysis system, because I think getting the prices down, I think there's going to become very soon where blue hydrogen is going to get a real run for its money with green hydrogen coming on at scale. But and I think we're going to need it all. We're going to need all. If we're going to really go to net zero by 2030, just do the numbers in Canada. We're going to it's going to be a big opportunity to go for both blue and green. And the kind of work that Kathleen's talking about opens up some pretty exciting opportunities if for being able to make blue hydrogen when you don't maybe have really good wind or solar resources or renewable resources, and you don't you want to be able to make hydrogen without using a lot of water and without having CCS storage potential. So it's all of the above, I would argue. Oh, you're on.
Yeah, here we go. Yeah. So we also use renewables, and we're actually even greener. And we have a low net CO2 as it is, but if we use renewable energy, it's extremely low. So we are very happy to collaborate with renewable growth, and we're sort of ideal in a power to gas type of program for storage for intermittent renewables, because we're much less expensive than electrolysis. So it's a it's an interesting niche.
You're muted, Nick.
Thank you, Max. So I said thank you, Kathleen and David, and also thank you, Shannon, Badr, Matt, Maggie, and especially thank you, Max, for being my sidekick. So what I'm hearing is we just have this amazing opportunity where we have a way to really bring our energy systems to zero carbon. Whether we take our natural gas, are unable to take the hydrogen out, we have some amazing technologies, and we can see how the green hydrogen side is just in such growth. So we're in an excellent position in Canada, especially Western Canada, to take advantage of where the world's headed. So I hope everybody enjoyed and had a good view of what is possible in Western Canada, because the future is very bright. And I think the more we can invest here and the quicker we can do it, the more dominant of a position we can take in the world, as the world is actually looking for a place to import their hydrogen. So thank you, everybody. And I just want to, I'll send out a post-event survey that I asked everybody to fill out. And as well, I'll send you a link. So we have podcasts, which each of our presenters, if everybody, we had a little snapshot of what they had to say, but we have a 20, 30, or some cases, I think with Maggie, I think it was 45-minute interviews. So if you want more details, you can definitely take a look at those. You can find those on our website, futureproof-network.com. So thank you, everybody. And yeah, thank you for making this a wonderful event.
Thank you.
Thanks a lot, Nick. Take care.
Bye.
Thank you, Nick. Thanks,
That was
everyone.
great.
Yeah.
Thanks for setting it up.